In this module, we will build upon the assembly language programming skills we developed in the first module. We will deal with constants, variables, add some data memory operations to our skill sets. Then we will use that to enhance the basic assembly language program a little more. After that, we will review some more instructions that take some other operands to just increase our tool chest of instructions we know in assembly language. And at the end, I will leave you with a few reference sources such that you can use that to build and enhance your assembly language programs. Have fun.
Okay, so let us try to work on our assembly program a little more. Let's make it a little more readable first. We have a concept of defining constants. Instead of defining numbers all over the place in a program, we can define a constant. So how can you do that in an assembly program? Well, the assembler provides a construct that you can use, provide a constant name, then space followed by EQU and a value. So an example is you can specify upper limit EQU 100,000, height EQU 20. After that, you can use the constant name upper limit everywhere in the program where you wanted to use that constant. And it helps you change that number in one place only, in the bottom of the program, somewhere where you will put it. Let's go to something more interesting. Variables. So how do you define variables? Well, you have to be able to define a place where you want your data to be stored. In programs, you can get a data segment defined for that. And when you run a program like this, the operating system will create a memory area which is called the data segment. And you can define your variables there. How do you do that? You can define a section first by saying section space dot data. This will define your data segment. You can only keep initialized data here, that is data variables that have a certain amount of data specified already. Now the variables themselves are specified in the following format. You put a variable name, space, the type of the variable, space, and the value then. The type of the variable tells how much memory should be allocated for this variable. You can define the type as a byte with db, define byte, then you will get 1 byte of memory space available. You want a word, you define it as dw. You want a double word, define it as dd. Quad word, define it as dq, and then you can define like 10 bytes together as dt. Here are some examples. So we put dot section space data. On the right side here, city db Cupertino. Now what this does is we're really defining a byte. But what this does is it defines a string as an array of bytes. So each letter is a byte. It really defined 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes individually in an array next to each other. Our db12, it's a byte number 12. You can define an array not just as a string, but you could define an array also by comma separated values. So prime number space db, we want bytes here, space 1, 2, 3, 5, 7, 11, 13. Other examples, you want bigger numbers, house count. You define with dw and say, okay, initial value 15,000. You can define a bigger one with double words, say you're counting a population, dd, and then 2 million there. Now keep in mind that all these numbers have an upper limit, and we work through that, and that is defined by the number of digits that are available in that amount of space. A double word is 32 bits, and 32 bits was about 4 billion in total range. Pi dd, it's a double, and we put a value of 3.14159. Now this is a special number, it's a float, and we are defining it float, and float numbers can be either defined as doubles or quads depending on the precision you want, and we are defining it as a double here. Now let us go back and look at our program one more time and try to put these constants and variables in the program. they will help make the program a little more readable. The bolded sections here show you where I have put the constants. So instead of the 1 billion, I put a loop upper size, and I put it as equals 1 billion. And instead of counting down to 1000, I put the lower size to be equal to 1000. And then I replace those values here. I also used a variable to define the exit code. Now, the syscall that we have here, the two statements before that, we set RAX register and the RDI register. The RDI register takes the exit code, which by default we would have put 0. But what we're doing here now, just to show, we set the exit code to be -1, and then in the program as a variable, we actually change 0 to this variable's value, and then that variable value is what we copy to in the move instruction to RDI. So now we just showed we can actually add constants, we can add variables in this program, and the assembler that we will use, and I'm using NASM, will convert it. So I ran the program, compiled it, linked it, and then I ran the program, and it ran in pretty much the same time, 0.34 seconds. So is there something more interesting that we can do still with this program? One more thing. So what if we, for the counter that we were running, instead of using a register for the counter, what if we were to use a memory location? And then every time we decrement that counter, instead of decrementing the register value, we were to decrement the memory value. So in this program, what I have done is I created another variable in the data section in the bottom and called it the counter. And I made it a quad, so I can fit large values. So it's a 64-bit number. Initially, I put it as 0. Now in the program, in the move instruction that I have highlighted as move in bold, that's where we initialize the counter with the value passed in register RDI. And after that, we will decrement the counter, and we will compare the value of the counter against the loop lower size. So these two instructions, now decrement and compare, are actually working against the keyword, and then I have used square brackets because we were really looking for the value in the memory location of counter. This program works just fine, except for one thing. So you notice the real time now to run this program became 1.879 seconds. That is a 5 times reduction in performance. So we, instead of using a register, we used a memory variable, and we got a 5x drop in performance. And the reason is that we are actually going and getting the data from memory and changing it, and we have to store it back in memory. Now the reason it is only a 5x reduction is because of a concept we will discuss later, which is cache. So the processor is still keeping it in the cache and not really going all the way to the memory. If it were every time, in every decrement, go back to the memory, the performance would have been much worse than this. But already you can see an example of why it makes sense to compile to values to registers. The registers are closer to the arithmetic logical unit, and if the value is already in registers, the programs operate faster. That is the whole purpose of having registers in the CPU core. So now let us move to a few more instructions. So we add a few more instructions to what we already discussed, and that will help you build more complex programs and also help you understand how to add more instructions yourself to your repository of instructions. So the next ones we are looking at are push and pop. We talked about it before when we talked about the stack pointer. So when you push, you move data from the data operand. So you will provide a data operand to push. That operand can be a register, a memory address, or it can also be an immediate data. And this instruction will move that to the stack, and then it'll decrement the stack pointer. And it decrements the pointer by the size of the data that we just pushed. Pop works the reverse way. Pop is going to move the data out of the stack to the data operand. So it copies the value of the memory location pointed by RSP to the data operand, then decrements the stack register RSP value by data operand size in bytes. Actually, it increments the RSP stack value because the stack decrements on push and increments on pop. Here are a few examples. Push RAX, it's going to push the value of the register RAX. First, it'll decrement the stack pointer by 8 bytes because you're pushing down a 64-bit register, so that's 8 bytes, and then it'll copy the 8 bytes to the memory location. Pop will do the reverse pretty much. So it'll read 8 bytes and then it'll increment the stack pointer. Now, you could also have a few other examples, like you could not push RAX, you could push the address on RAX. When you put a square bracket around it, it means push the value in the memory location defined by RAX. And pop will mean pop out the value to the memory location defined by RAX. And I think you should really be able to also specify the fact that you want a value as a byte or a word, so you define the data operand size. Or you can just do a push and immediate operand push 50. So more examples: shift and rotate instructions. So shift and rotate instructions move bits around in the byte or in the data that you use. Take an example here. Shift SAL and SHL are shift left, and the difference between A and H is shift arithmetic left versus shift logical left. There is really no difference when we do a shift left here. So look at the instruction SAL and then use the AL register and put a comma 1. The 1 after the comma tells you how many bits you want to push it by. So 1 means only push 1 bit to the left. So you have 8 bits already. You will push all of these to the left. So the leftmost will drop out. In this case, we have a number where the leftmost bit was 0, so it drops out. The dropped out bit goes to the carry flag, so the carry flag still keeps it. And on the right side, because you're pushing to the left, now you have a hole on the least significant bit. So what happens on that is you get a 0. So it'll hard put a 0 value there. So shift left moves 8 bits to the left, 1 gap is open on the right side, lower least significant bit puts a 0 there, and what pushed out and dropped out of the bits goes to the carry flag, the leftmost bit. We could also look at shift right. Now shift right has a small difference between shift arithmetic right and shift logical right. When you do a shift arithmetic right, similarly all bits will shift to the right. And in this case we are shifting the bits to the right. So the rightmost bit is moving out. So in this case we see that the rightmost bit is a 1. That drops out, and what drops out goes to the carry flag. Now what happens to the leftmost bit? So when we do a arithmetic right, what happens is the leftmost bit is kept the same as the previous leftmost bit. So if you had a 1, it'll stay a 1, and if previously you had a 0, then it'll stay a 0. So it does not change the leftmost bit, and the reason is it wants to do a signed. It doesn't want to shift your sign. If you had a negative number, it wants to hold that, and if you had a positive number, you hold that. SHR is a logical shift right, and pretty much the difference is that still the rightmost bit shifts out, goes to the carry flag. The bit that you put from the left, instead of being the same as the leftmost bit, is always a 0 in this case. So you just get a 0 hard into the leftmost bit. That's what happens when you shift right, and the difference between arithmetic and logical right. Let's look at binary arithmetic. These are simple: add, subtract, multiply, division, or divide, and then you get two operands, the dest and source operand, and these operate on the destination and source operands and put the results into the dest operand. So add RAX comma RBC is going to add RAX and RBC values and put the results in RAX. Subtract RAX 50 as the second example is going to deduct 50 from RAX. Let's go to some of the logical examples, logical statement category examples. And, or, XOR, not, these are the logical statements. These perform bitwise operations. So if you have a byte that you want to perform an AND operation on, the AND will be done bit at a time at the same offset locations between these two bytes that you provide. So if you do an AND, as in example 1, between RX and RCX, you have 64 bits each. It will do a bitwise AND across both of these registers, and the final number, the result, will be saved in the destination register, which will be the first operand. Similarly, OR will do an OR operation, XOR will do an XOR operation. NOT just takes one operand because it calculates the ones complement, which means it just flips the bit. It just needs one operand, it will flip the bits for that one operand. So a few more instructions now. Let's get to the category of bit and byte manipulation. The BT instruction, it'll test a single bit in the operand, and the way it tests it is you specify two parameters, two operands to it. The first operand will be the value, which data set do you want to test the bit on, and the second is the offset to find the bit, because if you have a 64-bit register, you want to know which bit are you working on. So in the first example here, we do bit RAX comma 10, which means the bit at the 10th location in the RX register. So what this operation will do, BT, is it'll copy that bit, 10th bit in the RX register, and move it to the carry flag. So it just moves it to the carry flag. That's it. How does that help? In another instruction, you will be able to test the carry flag and make some conditional choices after that. Now the other instructions that are a little bit more than BT are BTS, BTR, and BTC. The only difference between BT and BTS, BTR, BTC is what happens after you move the bit to the carry flag. And BTS will set that bit to 1, BTR will reset it to 0, and BTC will just complement it, which means if you had a 1, it'll become a 0, and if you had a 0, it'll become a 1. We'll go and look at some more instructions now, primarily that use condition codes. So before we go there, we have looked at instructions for jump before, and there were a lot of condition codes that jump uses, and jump is like an if condition. The condition codes across all these instructions, like jump, set, move, they're all the same, and they all depend and go and evaluate against the flags that are present in the R flags register. So here's a list of all the flags that I found in the reference, and most of them are self-explanatory, like A means above, AE means above or equal, B is below, BE is below or equal, C is an indicator of carry flag, E means equal, which is the same as a 0 flag being set. So this is the total set, and depending on what your logical condition that you want to evaluate, you will be using that instruction, those codes. And the way you use it is if you were doing a jump instruction J, and then you follow the condition code that you want to test against. Now let's apply this to the next set of instructions, which are set instructions. These are further the bit and byte. We looked at the bits, how to set a bit. Now we will look at the byte ones. So you can do set and then condition code. So set z will set the byte to 1 if the condition code for 0 is 1, which means the 0 flag is 1. Set e is the same as set z. Then set b is if it is below. But basically set takes all the condition codes, and you can, in the previous slide that I showed, and you can use any condition code with the set instruction. So basically the set instruction sets the value of the byte based on all the condition codes that you can use. So as we have gone through assembly programming, you will do it for fun. You will probably not be writing assembly programs other than that, but it's a good programming language if you want to understand core performance, what makes a program faster, what makes things slower. And when you want to really test basic concepts, assembly is really, really good for that. So what other resources do you have when you want to have fun with assembly, play around? One, you will need a compiler. You of course need a virtual machine somewhere. And I used NASM. There are others you can use, YASM, FASM, and you can choose the one you like. Then you need to know, okay, where are these assembly instructions defined? Initially, you will need to go to a good reference when you are going beyond the basic set, especially. I used the Intel software links to find them. It's in first sight not easy to understand what's written there. You have to get a little used to these, but then you get it. I also found a good reference that I've linked here, which is a book on assembly. It's really nice. It's free. You can just go to that link and read more about the language. I also found the same data that you have on the Intel sites in a more easier consumable format in another website. So I just put a link there for reference. But you can use these or other references if you want to do more in assembly. Okay, then good luck with that.